I hope my screen is visible to all of you. So let's start. Actually, my system has stuck, so that's why I joined with my mobile. Slowly start it. Okay, so let's discuss a bit about week 5. So in week 5, mostly we have done in quiz 1. Yes, Kiran.
Sir, what is the agenda of this session? Like, which weeks will be covered, and like only revision, or will you take some questions?
Sorry, your voice is not clear to me. What you are saying?
Okay, so let me just a second. Let me connect my headset.
I please check with the eligibility criteria. That is important. The ones so please check with the eligibility. Like, are you'll be eligible or not for interim? So I think you'll be eligible. So someone can answer. This will be more because I'm not sure. There is a issue. I know there is a problem with eligibility criteria. So please check with that.
Yes, sir. Am I audible now?
Yes, you're audible.
Okay, so what's the agenda of this session? Which weeks will be covered?
So we'll cover 5 and 6
Five and six. Only the concept summary, or questions will be taken.
with the questions also. We'll discuss questions also. So that's why I'm thinking to do problem on it here for week 5 because we many times this is now going to be thrice. So we'll discuss for week 6, which is SVD, I think. But let's do for 5. Let's do some problem. So there may be some problem, on the inner product also. So like as here, let me see, somebody is want to say something. Okay, so where is that? Yeah, actually, I'm not speaking. Just a minute. Okay. Okay. Sorry. So let's do some problem. So the main important thing in week 5 is uh, yeah, complex matrices are there. Anyhow, I think linear. there would be, orthogonality. I think it is. So mostly related question would be the diagonalizability of Hermitian matrix. And again, a bit confusion related to the inner product. So be sure with the inner product, how the inner product would be. So like I'm going to give one problem on this. Let's say I have two vectors, I 2 and 1 minus 2i. Okay, and another vector, let's say this is u, another vector v, which is of 0 minus I and 2i. So what is going to be inner product between u and v? What is going to be that? Can everyone solve this and let me know? This is an important one because inner product in real numbers and inner product in complex number are different.
2.
So this is going to be 2.
2, yes.
Okay. Okay. And let the others solve it. Then I will back to the Hermitian and Unitary and diagonalizability. To sound the same too. So easy because this I met the this was a concern in last time also in the last revision session ritual. So you have to do u sorry, u, there is a star v. So if you have such thing, then you have to do like this, u star v, where the hidden thing of star is u transpose or conjugate transpose or transpose conjugate is there. So if you do it here, so this is going to be the transpose is going to be the horizontally here. So this is minus I. So and the conjugate is going to be I of minus I. This is 2 exactly, and this is 1 plus 2i. And the second one is 0, and yeah, this is just I, and this is 2i. So if you multiply, this is going to be 0 plus, in place of plus, this is going to be minus 2i, and this is plus 2i, and this is going to be, if you multiply, this is what is going to be here, 1 plus 2i and 2i out. So minus 2i is there, then plus 2i is there, and is it 2 or 4? Plus,
Yes, it is 4, I think.
so 4, and then I would be minus 4.
Minus 4.
So many of you answer just 2, so I don't know. I think I'm making correct, right? This is correct. So this 2i is going to be cancelled. This is minus 4, the answer is. So yes, so many of you answer 2, 2. So I don't know what are the mistakes. Yeah, this is minus 4. Okay, so this is a, sometimes, the problems related to this is kind of, is this vector u and v are orthogonal or not? Sometimes the question would be of this kind, orthonormal, orthogonal. Sometime, so mostly question will be related to the orthogonal because these vectors are not orthonormal. So somebody is asked maybe what is going to be the norm of in this case. Maybe there is a norm, right? Maybe the norm is going to be different in this case. So norm of the vector, what is going to be in that case? So what all of you do it, this is a good thing, a good practice also. So what is going to be the norm here? Because once we done this, then there is nothing to I will just tell the concepts and maybe one problem. What is going to be the norm here of U?
Sir, can you show?
Yes, so let's do it. So answer, I'm not sure. So what is the norm here? Generally, the same thing we'll do. The norm square is, you want to find norm is, just do the norm square. And norm square is nothing but the inner product between U and U itself. This is what it is. And the U star U itself. And which is going to be the, again, I have to convert it horizontally. And previously it was, so this is going to be the same minus I and 2 and 1 plus 2I, right? And U is going to be the same as I 2 and 2 minus I. Now you have to multiply this. So this is minus I square is there. And this is plus 4. And this is 1 plus 2I, 1 minus 2I. So 1 plus 2I, 1 minus 2I is there. So this is going to be 1, right? Minus and minus is going to be minus and minus going to be 1. Plus this is plus 4. And this is plus 1 plus 1 and this 4 and minus I square again will come. So it will be 1 plus 4, right? I think it is correct. I hope all of you are getting it. This is A minus B and A plus B case. And now this 1 plus 4 is 5 plus this is 5, which is 10 here. So slightly different as we have in the real number. The inner product and the norm is going to be a bit different. Okay. So I think I am numerically correct. Please check. So this is going to be 1 minus 2I square. Yes. Yes. A minus B. This is nothing but A square minus B square. So 1 square minus 2I square. And this is what it is. So this is how, this is the meaning. So sometime, maybe orthogonality, sometimes, question would be asked, the eigenvectors are orthogonal or not, with the different eigenvalue. Okay. These are important. Sometimes the unitary, the question would be asked the differently also. Like unitary, we know, unitary matrix. We know the unitary matrix, which is nothing but if we are saying U as a unitary matrix. Okay. So it means the definition of unitary means U star U is, as the orthogonality case, U star U is going to be identity. That is what the unitary. But if you see the basic definition of it on between, if you have a matrix of n cross n and see the columns of this U matrix, sometimes question would be asked to distinguish, okay, so between the columns. So if you see the columns, so columns are going to be orthonormal. Okay, orthonormal, as the case of same, orthogonal matrix. You remember orthogonal matrix? The matrix, if you are saying orthogonal, it means if A is a matrix which you are saying orthogonal, means A transpose A is identity. That is what the right orthogonal. And if you check the columns of it, okay, of that matrix, they are orthonormal to each other. Means the vector, the columns, we have like a vector, and if you do the inner product between them, okay, and they are going to be give the 0. Similarly here the unitary, if you do the inner product between two columns, they will be orthonormal to each other. They will give the inner product as a 0. This is what the difference. So sometimes question would be asked on the columns even, and if you have a unitary matrix, then what is the relation between the columns? Some complex problem would be asked also. Okay. So that's why if you done with this, then no problem would be for you. Doing the inner product in complexes, if you very much clear, then easily and very easily, just do this. You just need to remember this one. U star V is nothing but U inner product U and V is nothing but U star V. If you remember it always, then there is no issue. Bit calculation would be there, but easily can calculate. Someone wants to say something.
The columns must be orthogonal, right?
So no, or not orthogonal, orthonormal.
Okay.
Why? The reason is because we are doing now U star U. So if you are saying the orthogonal, in that case you will not go. I will get identity matrix. You will get a diagonal matrix, but you are getting right size as an identity matrix. So that means the each columns, if you're treating as a vector, so it have the norm as 1. That's why if you do the dot product with itself, it will be 1. Getting it?
Yes.
So the reason of it saying to be orthonormal, you can say the orthogonal. Okay, but definition will not satisfy. It will be, if you are saying orthogonal, in that case you will get the diagonal matrix. Okay, because if you do inner product with itself, if it is not orthonormal, then it is, in that case it is going to be not going to be the norm 1. It's going to be the different norm. So that's why here the vectors, if you're treating the column as a vector, in that case it is going to be orthonormal, means one is step ahead between up from the orthogonal, just divide by the norm of the vector. So that's why this is important. If you do with this inner product, everything will be easy to you understand it, and to understand and even doing solving the problems. So this is what the orthogonal. Hermitian, let me tell you a bit about the Hermitian also. Maybe I just wrote wrongly here. Just a second. Okay. So there is one important thing in the Hermitian also. Okay, so Hermitian is a matrix. We generally say A is a matrix, and we call it as a Hermitian, or will is said to be Hermitian matrix. If you do A star A is equal to A, that is what it is. Okay, but it have, so you know already A star is a conjugate transport, but I want to tell a different thing related to it. Is sometimes question would be asked on the properties. So the thing is that as you have the property in the symmetric matrix, very similar property it have also. The thing is that here it is on the diagonals, it have real number only. And the reason you easily know it, if you do the conjugate transpose, the same number is going to be, means if you do conjugate transpose, when it will be not impacted on diagonal, the reason is when it will be real. So the diagonals always would be real, if you can easily check it. And the second property is not only the diagonals, it have the eigenvalues, okay, which is eigenvalues are actually real. This is one another property. Not only this one, another property is eigenvectors. eigenvectors with the different eigenvalue. These three properties are important. Okay, different eigenvalues. Eigenvector with the different means, I mean to say, if you have a two, so sometimes geometric multiplicity. So if you don't know, sometimes the repetitive eigenvalues you used to get. Let's say I am saying 3, 3, and 5. If you have 3 cross 3 matrix, so or maybe I and you got the eigenvalues as I, okay, repetitive I and 1. So in that case, maybe suppose for I you got two different eigenvectors, different in the mean to say two independent eigenvector. Okay, let's say let me write it. Suppose you have a matrix 3 cross 3 and you got the eigenvalues I and 1. Okay, so in this case here for I you got two independent eigenvector. So here is the thing is that these two may not be orthogonal. Okay, these two may not be orthogonal, but if you compare with the one, for the one whatever you got eigenvector for corresponding to 1, so if you check it, this is going to be orthogonal for both. So that is what I mean to say with the different eigenvalue. Okay, then eigenvectors are going to be orthogonal. Okay, this is what it is. Sometimes you will get the question, sometimes on the properties itself, on the property itself you will get such things. So if you know these properties, this will be easy to deal with. Sometimes question would be, so on the diagonalizability, let's discuss for the diagonalizability. Sometime one thing is there, we discuss for the diagonalizability, the Hermitian matrix is always diagonalizable. Okay, always diagonalizable. It is always diagonalizable. Okay, even no matter if it is a repetitive thrice, means let's say the eigenvalues I you are getting, still you will get two different, you will get always a different, I mean different in the case of three linearly independent eigenvector. In that case your matrix is always diagonalizable, right? You know it. The reason is you are able to convert your matrix. Let's say this is A, you are able to write your matrix as P inverse or dp, where P is the matrix formed by the eigenvectors and D is matrix which formed by the eigenvalues, where the eigenvalues lie on the diagonals. So this is, let's say this is here, this is P inverse is here for this one. So you know it because diagonalizability you did already, very exactly similar, only in place of real numbers you are doing on the complex number. That's all. So eigenvalues, eigenvector, finding the eigenvalues, eigenvector, all are same method, you will follow it. But the different thing is only the inner product. Otherwise rest all, everything is same. So that is what in the week 5. Let's jump to the week 6 only.
Sir, in week 6 SVD, can you explain from like scratch, like
Yes, yes.
step by step? Can you please explain? I'm finding a lot of difficulty with SVD, sir.
Okay.
So,
I will tell you one calculator also, which last time we had discussed one. I will tell you that
so,
you can easily verify always. Yes.
so please explain. Please revise the diagonalization of Hermitian matrix.
Diagonalization of Hermitian matrix.
Yes, sir.
So the case is that properties or with the example you are saying, I mean to say how to find the eigenvalues. These all.
Sir, Square's theorem and spectral theorem. I'm confused in that.
The which theorem? Source theorem and spectral theorem.
Yes, sir.
Okay. Okay. So okay. Spectral theorem is for the diagonalizability case. So okay, let me. So there is two theorems. So the case is these two theorem is came actually with the two reasons. There are two. So let me write that first. First is the Sue's theorem, and the second one is spectral. Okay. These two are for the different case, but for so there is a the different case was the reason is this came to simplify the matrices, means to convert our matrix with the simple representation. That's why these two theorems are there. The one common thing is that you need first square matrix. Both will work for a square matrix. So once you have a square matrix, so there is a possibility that your matrix is, first thing is, diagonalizable, and the question is that sometime your matrix is diagonalizable, sometime not. Okay, so there are two cases, sometime diagonalizable, okay, and sometime not. Okay, so if your matrix is diagonalizable, okay, so the spectral theorem gives the guarantee that if you have a symmetric matrix, okay, the spectral theorem is specifically for symmetric or Hermitian. Okay.
So it's one small question, sir. When you say diagonalizable, do you mean orthogonally diagonalizable?
So the case is, let me yes. So diagonalizable is for this is I'm saying for general matrix. Okay, but symmetric and Hermitian. Okay, this is for general. I will tell you that when it is going to be the orthogonally also. So
what is the difference between orthogonally diagonalizable and diagonalizable?
Okay.
So it will be unitarily diagonalizable.
Yes. So let me tell you. So some doubts are there on the diagonalizability and diagonalizable and orthogonally diagonalizable. Okay. So let me first discuss for the general case even. So suppose you have a matrix, general matrix. It's not saying, I am not specifying it is a symmetric, Hermitian, or any special matrix. Just a general matrix. It could be a zero matrix of order n, or could be anything. Not sure what is going to be the end, whatever the entry is going to be.
Can be M cross N?
Sorry?
Can be M cross N also?
No, not for M cross N. This is for square only.
Okay.
So let me tell you, we are discussing 5 and 6. So this week 5. So this week 5 is for square, okay? Square matrices. And week 6 is for general, means rectangular. Week 6 is for rectangular, okay? Means here the matrix is going to be of any order, M cross N. So because SVD is for, so SVD is for any rectangular matrix. So I will tell you that, let me give the differences, lots of differences here. So here is, see, these theorems are everything for week 5 and 6 are actually, we want to simplify our matrix. Okay, we want a different appearance of the matrix, but simplified version. Okay, so if our matrix is a square matrix, okay, then diagonalizability is there and upper triangular matrix is there. Okay, I will tell you where it is. When it is not diagonalizable, then we'll discuss that. Okay, so this is for a square matrix. Okay, now if you leave your square matrix, but you said no, I want a general any rectangular matrix. So okay, so we want to discuss for any rectangular matrix also. In that case, still we want a simplified matrix, means appearance wise, that is called similar matrix. Okay, the word is appearance is called word, the proper word in mathematically similar, is similar to other matrix. Okay, that is we have seen the math too, in maths too, but let's leave it here for the time being. So I want to this, let's say this is again a general matrix. Here it is not specified, any general rectangular matrix. Okay. So I want a simplified, means I want a version of a matrix which is called singular value, SVD, singular value decomposition. I'm converting this matrix, this general matrix A, in a singular value decomposition, that is called singular value decomposition of it, with the different appearance. Okay, the appearance is, let's say A is could be written as a some, I think Q1 sigma Q2 transpose is there, what something is there. I will verify it. I think this is correct, right? Q1 sigma Q2 transpose. Can anyone confirm it? Otherwise, I will confirm in the lecture.
Oh, yes, sir. Yes, sir.
Where let's say A is of matrix n cross m is there. I will back to here. Okay, I'm just giving a difference here at least. So here n cross m is there, so you can easily make it. First, you will make the sigma matrix as a n cross m as the matrix A have, the order. So sigma have the same order as A have. Now this is a matrix multiplication. Okay, so now you can fix the order of Q2 and Q1. So see, this is n cross m. So here is m is there. So that's why the order of Q2 is going to be m cross n. Sorry, not m cross n, m cross m. And here is n is there, then you can fix the order of Q1, which is n cross n. So right side, left side is going to be square matrix, and middle one is the same order as A have. This is the form called SVD, singular value decomposition form. Okay, so this is when the case is your matrix is rectangular. Okay, when matrix is rectangular, then we getting a simplified version of it, which is called singular value decomposition. Okay. But if your matrix is not rectangular, so this is for, so if your matrix is a square matrix, okay, then we talk about the different representation. Okay, I will tell you, if you do the singular value decomposition, okay, if you do the singular value decomposition of a square matrix, no, you will get the, you will end up with the diagonalizability. Okay, so please, you can check yourself. Suppose I have given a matrix. So this is, see, this is a rectangular matrix. No, your square matrix is also a kind of a rectangular. So if you do SVD of it, okay, if you do SVD of it, you end up with the diagonalizability, means the form of diagonalizable, as here this one. Okay, so that's why it is very specifically we used to study this in the rectangular case. If you do the square of the same diagonal matrix where you are getting here, the same you will get. There is no difference. Okay. So SVD is again, these all diagonalizability, upper triangular, and SVD all are simplified appearance for the matrix. That's all. Now this, let's back to the square matrix. Okay, if you have this matrix, so sometimes your matrix is diagonalizable, sometimes not. So why it is not diagonalizable, we have discussed a lot, because when your eigenvalues are repetitive, in that case the possibility means there is a problem to getting that many eigenvectors, and you are not able to form your PDP inverse matrix. This P you are not able to form means that many eigenvectors you are not able to get, and in that case your matrix is not diagonalizable. If you are able to get, then your matrix is diagonalizable. So someone have doubt that when we will say a matrix is orthogonally diagonalizable, what is the meaning of it? So there is one word associated with that. If your matrix P is orthogonal, that's all. If your matrix is orthogonal, then you can call it as a orthogonally diagonalizable. If your matrix is not orthogonal, this matrix P is not orthogonal, you know the definition of orthogonal matrix. P transpose P is identity. So if this P is orthogonal matrix, then you can call it as a orthogonally diagonalizable. Your matrix is orthogonally diagonalizable. If not, if your matrix P is not orthogonal matrix, then you can just call it as simply your matrix is diagonalizable. That's all. So I hope all of you are able to understand. You are able to understand the difference between diagonalizable and orthogonally diagonalizable. Only just related to this P matrix. Okay. Now, if your matrix is not diagonalizable, okay, still we want a simplified version of it. Okay, appearance wise, means that is called similar matrix. So simplified means, so we'll discuss. So now here the Sue's theorem came. Now your matrix is Sue's theorem actually here. Sue's theorem, if you see the statement itself tells that any word is there, any square matrix, okay? It is not specifying anything. Just say any square matrix is similar to upper, okay, triangular matrix, okay? It is not specifying any. If you have a square matrix, okay, then you will always convert that matrix in upper triangular matrix. The algorithm, you can check from the, I will discuss a bit, but you know already how to convert that. That is the algorithm. Step by step you have to follow that algorithm, and in lecture very clearly sir said how you will follow that algorithm and done an example. But many people have doubt on this theory itself. So the theory is that any square matrix, okay, it says any square matrix. So let's apply this for if your matrix is not diagonalizable, because if your matrix is diagonalizable, no, if you apply Sue's theorem, means if you try to convert your matrix in upper triangular form, again it will end up with the diagonalizability form. All of you are getting it or not? If your matrix is diagonalizable, okay, if you apply Sue's theorem, means if you follow the algorithm of Sue's theorem, what you will get, you'll get end up with your diagonalizable form. That's why let's do this for not diagonalizable case. Agar if you do for diagonalizable case, means your matrix is diagonalizable, and if you follow the algorithm of Sue's theorem how to convert that in upper triangular, you end up with this form only. There's no difference. Same as I am saying, no, if your matrix is diagonalizable and if you follow the algorithm of SVD, you end up with the only diagonalizable case, this one. So these are the differences. Means then these, if your matrix is not diagonalizable, let's get, we want a simplified version still. So in that case, apply the Sue's algorithm, Sue's theorem, and try to convert in upper triangular form.
Sir, any Hermitian matrix is orthogonally diagonalizable is spectral theorem.
Yeah, so I will still till now I didn't discuss the spectral theorem. Spectral theorem is specifically for symmetric and Hermitian. Yes.
Sir, that's my doubt was spectral theorem. If we define for Hermitian, automatically it works for symmetric, no sir?
Yes, it automatically, the spectral theorem itself says if if you see the statement, so please sometimes, means always, if you are doing in mathematics, very slowly, very clearly, and one by one word you have to read out for the any theorem. Okay, it says any symmetric matrix or any Hermitian matrix. So let's do for the symmetric only, for spectral theorem for symmetric matrix or real matrices. So any symmetric matrix is orthogonally diagonalizable. That is your spectral theorem for real matrices. Real spectral theorem for complex matrices is that any Hermitian matrix is unitarily diagonalizable. That is what your spectral theorem for complex matrices.
Okay, sir. And one more thing, sir. In Hermitian matrix, the unitary matrices will be columns of the eigenvectors of.
Eigenvectors.
Is that that only, no, sir?
Yeah, that is what I said, no, Hermitian. So if your matrix is Hermitian, I said no. Then there, okay, I think I told you that if your matrix are Hermitian, the eigenvectors are orthogonal. I said, I think earlier I said somewhere.
Okay,
when I was discussing the property of unitary and Hermitian. Yes, here it is. I think somewhere. When you have your matrix is Hermitian, in that case, your eigenvectors are orthogonal. You can you use it to convert in orthonormal.
Okay, sir.
Okay, so is this clear to all of you? The Sue's theorem, the diagonalizability, the spectral theorem, the SVD at least. These are the stepwise differences.
Sir, SVD, could you take an example and explain step by step, sir? if possible?
Yes. Yes. So at least all of you able to distinguish it. The differences, SVD, diagonalizability, SUS. If you not, I will repeat it again. Okay. So let's move to, so this is all about the diagonalizability and the SUS theorem. So I will back to the SUS theorem algorithm. There is that, I think if you go with the example, so there is no calculator, I think, to convert in SUS, but I have the calculator. Means I will tell you, I will show you one. I'm not promoting it, but for practice, I am saying you should to practice it. If you practice, if you are stuck in, you can put in the calculator and check. Okay, this is what the SVD. So SVD is again, if your matrix is as we are doing for the diagonal square matrices, diagonal. If it is diagonal, then fine. Not diagonalizable, apply Su's theorem to convert in upper triangular matrix. Okay, this is what it is. But we did for only square matrices. What is going to be the case for rectangular matrices? So that is what the SVD comes here. Okay, that is what the role of SVD, and it is also we want a simplified version of the rectangular matrices also. So in that case, SVD comes, and just now I discussed that SVD form is this one. This is what your SVD. So the Q1 is also a square matrix of order n. Qt is also a square matrix of order m, and the middle one is the whatever the order the rectangle it is. So whatever the order of A have, that is what the order of this sigma have, n cross m. Now how I will get this Q1 and Q2? This is what it is. The problem is how we'll get that our Q1 and Q2.
Sir,
So, yes.
Sir, in the lecture they explained Q1 and Q2 something to do with eigenvectors of A transpose and A transpose A. And they are saying that both of the eigenvalues of A transpose A and A transpose will be equal, but the sizes are different. No, sir. How can the number of eigenvalues only won't be same?
So the number of eigenvalues are going to be same in the case of non-zero. Sorry, number of eigenvalues are different. The the eigenvalues are going to be same for the non-zero eigenvalues. So yeah, this is very well. So the case is that if you have this one A matrix is then the A transpose, you will find it. Okay, and the order of it is going to be, let me write n cross m cross n. The order of this A transpose is going to be n cross n. Let's say I am saying n is greater than m. So this is a bigger one, and A transpose A, let me write it. This is going to be m cross n. Okay, this is n cross m. So the order of it is going to be m cross n, and this is the smaller one. Okay, but generally no, there is a theory if you have of such cases, no. So the case is that surely here the eigenvalue. So this is the number of eigenvalue it have more, and here the eigenvalue have lesser. Okay, but the rank, we check the rank. Okay, rank is always going to be less than or equal to m. Okay, you can always verify it. Okay, rank is always less than or equal to m. Either it could be m or lesser than m. Okay, so that means this matrix have what? Zero. Most of the zero eigenvalues. So many zeros eigenvalues. Maybe how many? That many numbers of it. N minus m. Maybe if it is your rank is lesser than m, in that case it have more. So what is going to be in that case? The non-zero eigenvalues, whatever it have, okay, non-zero eigenvalues. Let me, I'm writing these are the sign of non-zero eigenvalues, and these are the, let's say, zero. So both non-zero eigenvalues, whatever the both matrices have, they are going to be same. Okay, means in the numerically they are same even. You can check, I think.
So, sir, all the non-zero ones will be same, and the number of eigenvalues that are left for the n cross n, they'll all be zero.
Always zero.
Okay, sir.
Simply the reason is that, the reason is there is a theorem related to that. If you have a matrix of, let's say, 3 cross 5, okay, if you find the rank of a matrix of it, then you cannot say the rank of this matrix is 4 or 5. It never be. What is going to be the lesser order, in this case here? Here is the rank of this matrix A is always less than or equal to 3. This is just a theorem. You can remember it always. So it is so in this case, if it is making this order, okay, here the order, and I am saying the both non-zero eigenvalues are same, then in that case only the zero eigenvalues remain. So which have the higher order, it have that many zero eigenvalues. So because of these reason, you can answer it. Now the case is that, so if you find the eigenvalues of it, so where it will seem to form which one? It will feel to form this order, right? Q1, because it have that order of eigenvector, correct? So it will form, so you will find the eigenvectors here, and it will form the Q. So whatever the eigenvector, let's say v1 2 till vn you got eigenvector, and that will form the Q1. I think it is correct, right? If not correct, please stop me if you know theory a bit. Okay, v1, that till it will go vn. Okay, and now what is going to be the order for to find how? So next steps, so by this way you will form Q1. Okay, that is fine. By this way you will find Q1. How will find Q2 now? So either we can go with this one. Many theories are there, not many. The two theories are mostly. Many people have doubt on this. Either, so how we'll proceed? Either go with this one, or there is a singular value related to this. So whatever the eigenvalue it have, so we will find the eigenvalue of whatever the eigenvalue we got here from this A transpose. Okay. So what is that formula? Anyone can tell? What is that formula to find that? There is a singular value, right?
Sigma y is equal to ax.
Ax is equal to
Sigma y.
Lambda x. Lambda x.
Sigma
lambda x. No.
Sigma y.
Sigma
y.
This is what is. This is v. Let's say this is v, because I can vector.
Before we go to this one, sir, they said that sometimes if they're not orthonormal to each other, we have to use Gram-Schmidt process.
Gram-Schmidt process.
Sir, but with Gram-Schmidt process, if you give some vectors, there's so many different orthonormal bases, no, sir?
If you, sorry?
If you give two vectors and ask to take out a orthonormal basis from these vectors, many different orthonormal bases are there, no, sir?
Yes.
So I'm a bit confused there, sir. How do we use Gram-Schmidt process if the vectors are not perpendicular to each other?
If the vectors are not perpendicular to each other, then we'll try to convert using those vectors. We'll try to convert. So the case is that, the case is generally what the Gram-Schmidt does, you are not randomly finding the vectors to, you are not randomly converting using these vectors. You are converting in, you are applying the Gram-Schmidt process and getting the orthogonal vectors. Not only Gram-Schmidt give the orthonormal.
So, sir, in Gram-Schmidt process, we take V1, V2, V3, and we do Gram-Schmidt process.
Yes.
So, does the order of the vectors matter?
Yes. Because orders actually matters here. If you are writing this V1, then V2 is accordingly you will write, because once you got there, you'll use to feel it for Q2, right? So because and the second reason is whatever in the sigma you are writing in sigma is accordingly as you are filling here for eigenvector for this side, and for Q2 also you'll for feel like that, so that here the eigenvalues also you have to maintain, right? The order means for which one you are writing the first eigenvalue, for which one you are writing the second. This all you have to maintain.
So, sir, can you give an example where you explicitly we have to use Gram-Schmidt process, and worst case scenario where can you like give an example, and can we work it out, sir, where we use Gram-Schmidt process as well?
Yeah, let's do one problem, mate. Even we have some calculator, even you can use it. So just a second. So you can see this Gram-Schmidt is a bit longer. So that's why generally it is
Sir,
given
not Gram-Schmidt, sir. With SVD, can you explain
Yes.
SVD? Yes, sir. Preferably rectangular matrix, because that's a little more difficult.
What's the question?
Sorry, I think where it
No,
is.
what's the doubt?
Sorry.
What's the doubt?
SVD.
In SVD?
In SVD, how will we do SVD from A to Z? The whole process.
Like with the steps to solve it?
Yes.
Let me write the random here. Okay. So let me see it how even I never used this one. So let me take an example, then it will be easier to to skip. I will write the steps also in my side. Let me see it how it is calculating. So let's say this is 1 and 1. And I have just calculated of SVD of it. Okay, so our matrix is, let me write it here. So our matrix is 0 1 0 1 minus 1 0. I just randomly wrote here minus 1 0 and 1 1. So this is our matrix. Let's say this is our matrix A. So we'll find A transpose first. So here the matrix is 3 rows and 2 columns. So A transpose have order 3 cross 2, 2 cross 3. So it have 3 cross 3 order. So if you multiply it here, the matrix will get here. So let me see it here. It is actually work out the example also. So is this done here? For find the angular values of this, the detail is here. Okay, A transpose A. For A transpose, is it done? Find the U, just detail. Okay, he did for using this one. So he first found in the calculator, he first found the A transpose A. So if you do it for A transpose A, so let's do it here. So if you do A transpose A, the matrix is going to be, let's do the transpose here, 0 1 minus 1 0 and 1 1. Okay, and now this is the transpose one, and the A is exactly 0 1 minus 1 0 and 1 1. Okay, let's multiply it here.
Sir,
So
transpose.
How is it transpose, sir?
So
sorry,
it's not transpose, sir.
sorry, 0, 1 minute. Okay, so
0 minus 1 and 1 is the first row.
0, 1 minus 1, 0. Sorry, minus 1, 0, and this is 1, 1. Sorry. Now, if you multiply it here, this is 0 plus 1. Okay, that's why it is a bit. Okay, this is 1 here. And 0, this is going to be 0 plus 1. And it's multiply it for this one. This is going to be 0 plus 1. And here 1 plus 0 plus 1. So this is going to be 2, 1, 1. So if you find the eigenvalue of it, now I am going to skip. So the step is exactly 2, 1, 2, 1. So eigenvalue, if you found it, so eigenvalues is going to be 1 and 3. So I am going to skip this calculation. So it's your work. You have to find the eigenvalues. So
Yes.
I am writing eigenvalues is going to be lambda 1 is, let's say, 1, and lambda 2 is, let's say, 3. So not let's say, if you calculate, you'll get here, and that's why I am using this calculator to move fast. Eigenvalues are here. It is calculated. Okay, and how it is calculated, you can check it here also. Everything is written here, a minus lambda I n. You can find the root is all here. It is mentioned. And eigenvectors corresponding to 1 is minus 1 and 1. So I'm so this is going to be minus 1 and for this one. Okay, and
1 and 1.
1 and 1. Okay, minus 1 and 1, and for this one, 1 and 1. Okay, yeah. So once we got this, the next step is what? Once we found this, so either we'll go with the reverse case A transpose. What is going to be the case when we'll so this eigenvector is this one. So this will form our Q2, right? This is what our Q2. Q2 have so many times, if you are doing it, let's do it here. Let's write the form here first. Q1 sigma Q2 transpose. Okay, and Q2 have order. So this is Q2 have order 2 cross 2. Q1 have order, just now we calculated, no? Q1 have order 3 cross 3, because this is of 3 cross 2. This is what the order it is. So right one is going to be of 2 2, left one is going to be of 3 3. So eigenvectors we got, this will help to find Q2. So Q2 is going to be our, just fill out this eigenvector as a column wise. Minus 1, 1, 1, and 1. We got Q2. We want to find Q1. So Q1. So Q1 is, now we'll use the singular value for the timing. Let's use then back to this A transpose case also. We'll use this one also. And
In this is, sir, in this, is there any preference for the greater eigenvalue vector?
Greater eigenvalue means the bigger matrix or smaller matrix?
No. When we form Q2, then columns should be like lambda to eigenvalue.
So here is I use, so not the bigger and smaller. I didn't follow. You can write the okay. So I'm not following any order. If you are issue with this one, let's write for the time being. Here is 1 1, and here is minus 1 1. But the sigma you have to fix. So here you have to write 3, and here you have to write 1.
Yes.
Sir, here we have to use Gram-Schmidt process, no, sir, and normalize it and all. But we skipped that.
Okay. So this is already orthogonal. I didn't normalize it. Okay.
Sir,
So here
assuming it was not orthogonal, then we'll use Gram-Schmidt process and get the other two vectors.
or in the orthonormal case. Sorry. So this is one thing is there. The vectors, this is going to be a symmetric matrix always. Okay. This matrix is symmetric matrix always. Okay.
Right.
So this matrix is symmetric matrix. So using this spectral theorem, these are always going to be orthogonal. You have to convert in orthonormal. So you always check with that if it so the vectors are going to be orthonormal. Yeah, the case is that sometimes the repetitive eigenvalues will get. Let's say here you got suppose 1. In that case you may not be. So in that case we have to follow the orthonormal. Yes.
Okay, sir. So here, could you please explain again why both of these will always be orthogonal together?
Because this matrix is symmetric always. Even see, if I multiplied, still you got the symmetric matrix. So the reason is, there is a theorem. If you have matrix A and if you are doing A transpose or you are writing A transpose A, these matrices are always symmetric matrix. Okay.
Okay, sir. And symmetric matrices, the eigenvectors are always orthogonal to each other.
No, but with the different eigenvalues.
Sorry,
Means
distinct eigenvalues, distinct eigenvectors. They're always orthogonal to each other.
orthogonal to each other.
Okay, sir. So, and in the case where there are repeated eigenvalues, then in that case we have to use Gram-Schmidt process to produce
convert
another basis, another vector for the basis.
for the you have to get the orthonormal vectors.
Okay, sir. Could you please give an example of that, sir? That would be helpful.
Okay, but I just generated this one. I'm not sure.
Okay, sir. But in exam, will it come, sir?
It may come. I'm not sure. I'm not giving surety that it may not also.
But theoretically, sir, we just have to. So suppose if there is if there two, one is repeated twice, and we have two of them, how to produce the third one? Gram-Schmidt process only, no, sir?
So yes, using the Gram-Schmidt means no. Suppose you produces the third. So now from here you have to produce the third one, right?
Yes.
So for the finding Q1.
Yes.
In that case, what you have to follow, you have to take the first independent. You have to find a vector which is independent of the given two.
Okay.
And then once you found the independent, then you have to apply the Gram-Schmidt to convert these three independent to orthogonality.
Sir, if there are three, okay, the two independent ones, and then we
surely you have to see here it is you got only two, so third one you have to find independent, right? Now we'll use the singular value. What is that singular value? The way AV is equal to 1 upon lambda, right? Root of lambda. What is that singular the sigma? 1 upon root of lambda, and this is y. This is what it is, right?
Yes.
This is, let's say, vi, and this is, and now we want to find this yi, correct? These are the vectors we have. Yes, this is what let me see it once, the algorithm. Just a second. See, the procedure is here. Find the eigenvalues of A transpose, which we found. Using the eigenvector, form the orthonormal basis of R2. Okay, which if it is not, then convert Gram-Schmidt, use the Gram-Schmidt to get the orthonormal. If it is already there, which, okay, the case is that if you're symmetric, it is always symmetric. By chance you are getting different eigenvalues, distinct eigenvalues. In that case, there is no use of it. It will always you will get always the orthonormal vectors here. Okay, so if it is the same, then you have to follow the Gram-Schmidt to get it. So here it is written to form the orthonormal basis of R. Now use this sigma I or II ax, and this is y, where this x1 x2 is The basis of that is what the basis of already we got. This x1 is the orthonormal basis. Okay. To find the y1 and y2.
So matrix of eigenvector will be Q1.
Matrix of eigenvector. See, this Q2 is orthonormal. These vectors will come. If they are not orthonormal, you have to find the orthonormal vectors and then come. Means if these, suppose these two are not orthonormal, then apply Gram-Smith. Okay, and then you will get some other vector. Orthonormal
No, sir.
vector.
I'm saying it will be Q1, no?
So it will be Q2. This will be Q2, right? Now,
No, sir.
uh,
In the procedure, it is written as Q1.
Q1.
is it written for Q1?
A transpose.
For A transpose A, I am saying. We are proceeding with the A transpose A. We are proceeding with the A transpose A. See, this is simple. No, this is the confusion is if you are getting, just write this form. Whatever the order is, that will fill the matrix, right? That's why it will filled in the Q2.
Yes, sir. It's Q2.
Clear? Because whatever the order, this order will be fixed by the whatever the vector you got, if it is in R2, R3. So if you see the formula even, this is what it is written here. So Q1 is your see, this Q2 is your this vector x1, x2. Whatever you got here. Q2 is filled in this Q2 is filled by x1, x2, and this y1, y2 is actually after this singular values you will get here. Okay, is it clear with the algorithm?
Yes. Yes.
And still you have a doubt. Okay, if you are still doubt, just write this SVD and fix with this one. With the order, it will this order itself tell you where this vector will be filled. Yeah, you are getting this of this vector is column vector of 2 cross 1. This is 2 cross 1. So this order you are filling it here. So they will get 2 cross 2, which is very much clear. It is actually give the Q2. Clear? So if you're not forgetting with this, just remember the order here itself. The importance of order, you can see it. Okay, now let's follow this to find the singular value. So singular values is nothing but 1 upon lambda. Now let's find the y1, y2, and the next one. So let's do it here. So here it is. We have to follow it. So our matrix is 0, 1, minus 1. What is that? Our matrix is 0, 1, minus 1, 0, and 1 and 1. Okay, that is fine. And we converted it orthonormal. I just missed that, but you remind me. So we converted here in the orthonormal. Okay, so let's write here 1 upon root 2 minus 1 and 1. And this is equal to the singular value, which is 1 upon lambda. So we are doing for singular value lambda 1 because this vector is for lambda 1. So 1 upon lambda 1 and y1. So if you multiply it here, we'll get here. This is nothing but y1 is equal to the vector will get. This is 0, 1. If you multiply it here, this is going to be minus 1. 1 upon root will be out. And if you multiply, this is 1, just 1. If you multiply, this is 0. So y1 we got this one. Okay, this is for the sigma 1. Let's do for sigma 2. So again, write the matrix. So this is a 0, minus 1, minus 1, 0, 1, and 1. Now the second eigenvector is 1 upon root 2, 1, 1 is there. 1, 1, okay, is equal to the singular value, which is 1 upon root of lambda 3. Okay, sorry, lambda 2, which is root of 3.
Sir, is it 1 upon or simply sigma y2?
Sorry.
Is it 1 by root 3 or root 3? Root 3 y2. I think in the formula sigma y2
Let
was
me.
there.
This is 1 upon. This is just a sigma. This is just a
Okay.
sigma. If you see the sigma, this is, if you see the formula, this is what it is. And
So
sigma is nothing but of 1 upon eigenvalues, 1 upon root of eigenvalues. This is what it is, right? Singular values are what?
sigma is root of eigenvalue, right, sir?
Yeah, sigma is root of eigenvalues. Let me check it once. Yeah, that is what it is.
So you have put 1 upon root of.
Just a second.
So
Where-
y1 is equal to 1 by root 3 into. So sigma y1 is equal to
so 1 minute.
sigma
Singular values
y1 is
are
equal
root
to
of
x
root of
hat.
1 upon. Just a second, one second. Maybe I missed that. Okay, let me check it once. It is actually clearly mentioned. So sigma is a singular values. Oh, sorry. So sorry. So this is not 1 upon. Sorry. So maybe I just wrongly wrote. This is not 1 upon. This is just root of it. So sigma is just root of the eigen values. So here it is 1 upon root I just wrote. This is just a root of 1. So here it is just a root of 3. So these are the singular values. So this is root of it. So now from here y2 you will calculate here. This is y2 is now 1 upon root 3, and again 1 upon root 3 is there. So root 2 is there. So this is root of 6. Okay. And now we will multiply here. This is minus 1. This is again minus 1. And this is 2. Minus 1, minus 1, 2. Yes. See, now you got y1, y2. I need third one. So because we want, so we are forming Q3, right? Sorry, Q1, which is of, one column we got, second column we got, but third column, how we'll get the third column? What is going to be here? So the third column, y1 is here, y2 is here. The third one, first you have find independent, and then or Graham-Smith we have to apply. So first find the third one which is independent of these two. So how we'll get independent of these two? So hope you remember the method is -1, 1 and 0. Okay. Write the first vector as this one. Second vector is -1, -1 and 2 is there. Okay. So now change, so apply, Gauss elimination, means RRE of, if you apply it here, this is -1, or maybe we're multiplying it with the -1. So 1, -1, 0, and this is again 1, 1, -2. Now next step, in the next step you can subtract it here. So this is 1, -1, 0, and this is 0. If you subtract it, this is 2, and this is -2. So in the third vector, what you can assume? Here is 0, here is 0, and here is just 1 if you assume. So this vector is going to be ortho. So these three vectors are independent. So means checking to be this way you can check to which one, how I can get the third vector. So third vector you can assume now y3 as 0, 0, 1, which is independent of these two. By this way you can verify it also. By this way you can verify that these three are independent now. But you are not sure that these two are orthogonal or not. So now we have to apply the Graham-Smith to get it. So the work is still remain. So we got three vector, but we have to find the Graham-Smith. We have to apply. Once you apply the Graham-Smith, you will get some three vectors here, and then just fill in the here three vectors, whatever you got. Just fill it, and you will the final answer. See here the word is written. So here is let y1 to be the orthonormal basis obtained by from here. So you have to find the orthonormal.
So, sir, we just have to extend it with the arrangement process. That's it.
Sorry, I got disconnected. Am I audible?
Yes, sir.
Yes, sir.
Yeah, sorry. I don't know when I got disconnected. Many of you have lost. Let me present my screen to him. So I was telling the steps to find in SVD, to do in SVD. So we got these two. So we have to find the third one. Now we have to apply the Gram-Schmidt to orthogonal vectors to get, we have this three vectors. Y1 is 1 upon root 2 minus 1 minus 1, sorry, minus 1 1 0, and the second one is minus 1 minus 1 2, and the y2 is 1 upon root 6 minus 1 minus 1 2, and y3 we got by random, not by, we want to three independent, no, so this is 0 0 1. So now we have to find the third. So we have to convert this. We have to apply the Gram-Schmidt. So Gram-Schmidt says that take the first one and divide the first vector. Let's say I'm saying u1. u1 is nothing but y1 divided by the norm of 1. So this is already in the norm 1. That's fine. So this is already of norm 1. So this is y1. Sorry, u1 is nothing but your y1 because it is already of norm 1. You can check it. So 1 upon root 2 minus 1 1 and 0. It is fine. The second one. Yes, someone wants to. Okay. Okay. So now the second one, y2, or sorry, u2, to get the orthonormal one. u2 says what? You have to. What is the way? What is the formula of Gram-Schmidt? Anyone remember it? Inner product between y2 and 1 minute. The way it is, have to do the projection. The project using the projection formula. It is y1 we already got. So y2 and then sorry, from y2 you have to subtract inner product between y2 and u1 outside u1. This is what the formula. So y2 we have this one, 1 upon root 6 minus 1 minus 1 2 minus inner product between y2 and u1. So inner product between y2 minus 1 minus 1 2. So this is a bit lengthy one. See how it is, how long it is slowly becoming. Okay. So I will skip it. I will write the third one also, the outside u1. So by this way, and in the last you have to divide by the norm of the final vector, and you will get the u2 finally. And third, u3 is still remain to get it. So which is y3 minus y3 inner product u2 outside u2 minus y3 inner product u1 outside u1. This is using this bigger formula. You have to find u3. Once you got u3, this will form your q1, which is u1, u2, and u3. So finally, single, all you got, q2 you got, q1 you got, and sigma already, which is 1 3. If you're following the order of that one, you can check it which order we are following. So this is 1 0 0 3 0 0. This is sigma, this is q1, q2 already we have. So if you want to check it, here it is in the calculator. So let me show you in the calculator. It is actually found the three independent. So see, u1 is this one, okay, u2 is this one, and the third one he got, which is orthogonal, this one. And now he filled in this one as a q1, and this is for q2, sorry, this is sigma, and this is your Q2. This is how it is done. Am I audible? Am I audible? Okay. Okay.
Yes.
So this is what it is. So many steps are there. So the answers are we slowly reaches to the correct answer. Okay, you can match it here. We got for eigenvalues we already taken. So Q1 is whatever you can verify it here. Where is that? This is your Q2, which we have already found it, and this is the singular values are actually, sorry, I missed that. These are the singular values. The sigma is not exactly on where is that? Sigma is not eigenvalues, root of the eigenvalues. So singular values will be filled in the sigma. I just missed that. Okay, and this Q1 is a bit lengthy to find it. So in place of finding it, many people usually find by the method of A transpose. Using the let's find the A transpose A, eigenvector of A transpose A. So this calculator is actually did as the usual method we've seen is, but sometimes we directly used to find this Q1 from the eigenvector of A transpose. So we have A0 1 minus 1 0 and 1 1, and A transpose is going to be 0 1 minus 1 0 and 1 1. And if you multiply it, you will get the order of 3, square matrix of order 3. This is going to be 1, this is going to be 0, and this is going to be 1. This is going to be here 0, this is going to be 1 here, this is going to be minus 1 here, and this is here, this is 1 here, this is minus 1 here, and this is 1 here. Now if you calculate the eigenvalue of it, let's quickly calculate it here. 101. So I will use the calculator to do fast. Sorry. 0 1. Okay. 0 1 minus 1. 0 1 minus 1. Okay. 1 minus 1 and 1. 1 minus 1 and 1. Find the eigenvalues, eigenvectors. So let me see the diagonal of it. So eigenvalues are going to be 1 1, this one. Eigenvectors are going to be here, this. But still it is not in orthonormal. If you do the orthonormal, you will exactly get this one. To the Gram-Smith here, we have, if you do it here, it will be filled it here. Because if you check the eigenvectors are this one. 1 1 1. Okay, so 1 1 1. And I think eigenvectors are not orthonormal. So you have to convert in orthonormal. Means Gram-Smith anyhow I have to apply, and finally you have to get it. So these vectors, you can check it. This is this one, this one. These two are orthonormal. Okay, these two are orthonormal. What about this one? This is minus. This is minus. Okay. These vectors are orthonormal, I think, because these all are, yeah, these are distinct. So orthonormality is there. Okay, these vectors are orthonormal, but it is not in the form of, or sorry, orthogonal, but not in orthonormal. So using this vector, you will fill to the find the Q1 here. In place of going by this longer one, if you just divide by the norm of each, exactly you will get this vector here, whatever you got. See, if you divide by the norm here, root 2 will be there. See it, if you see here, root 2 will come. Okay, if you divide by the norm of this one, This will be exactly the same always. Root 3 will somewhere and root 6 will somewhere. This is 1, 3, root 3 it will give. And what about this one? This is also root 3 will give. And root 2, root 3 is done. This root 6 is not. We'll get the root 6 here. No? Anyone can check? This is root 2, 1 upon root 2, 1 upon root 2. This is 1 by 2, 1 by 2. And this is 1, 3. 3 will get. Yeah, this is again 3. Here it is not coming. Exactly. See, there are so many steps still there. The case is that you have to finally verify that after multiplying this all, after writing of this form, are you getting this matrix or not? This is the final step. If you are doing it, okay, SVD is going to be, yeah. By this way, you may get this Q2, sorry, Q1 is the different by whatever the method is given here or whatever we did, the same method we did. By this way, you may get different Q1 from here, whatever this A transpose method. If you follow, you will get different Q1. But finally, if you're multiplying all three matrices, you are getting exactly A matrix or not, you have to verify it. If you are getting, then both answers are correct, because Q1 is not, you are getting Q1, you are randomly choosing a vector and then making orthonormal. So that's why Q1 may differ. Q1 may differ, but you have to verify finally that if you are multiplying it, your answer is getting correct or not. That is your final answer. Okay. So maybe Q1 may differ, as here we are also. That's why I did here. That's why I did this method and also by A transpose, because you may get differ Q1 differently. Okay, Q2 may be same, but Q1 may differ. But if you do the final matrix multiplication, the final A, if you are getting, the both answer actually correct, because the reason is you are choosing randomly. To find the Q1, you are choosing a vector randomly and then doing the Gram-Smith. Okay, so that's why the answers may differ, but finally you will get at least A exact in both cases. So SVD forms are not only one unique. You will get the different singular values decomposition. Okay, so be sure with it. Okay. Now last is the positive definite. Let me finish it. Positive definite matrices. The first is quadratic forms. So see how the so first of all, is this clear? This SVD is clear to all of you? The method. Okay. So singular values are just going to be the root of the eigenvalues. How you will find Q1, how you will find Q2, and both ways I actually told you very quickly. I told you, but who is actually continuously seeing it can catch it. Okay. A transpose also give Q1. So best ways, this is many times doing this Gram-Smith. The best ways, find A transpose A for Q1, find A transpose eigenvector of A transpose to find, sorry, for Q1, sorry, 1 minute. To find Q2, follow the A transpose A, find the eigenvector of it, you will find Q2. To find Q1, find the eigenvector of A transpose and do the orthonormalization, write in as the vector, means matrix Q1, Q2. Yeah, you just multiply all three matrices and quickly check that you are getting exactly A or not. If you are getting it, your answer is correct. Someone may get different representation, but if he is also getting, after multiplying, getting the correct A, then that is also fine. He may follow the different method. That's why you're getting different. So SVD is not only unique representation, it have different representation. Okay, so don't worry with it. Answer may differ. Okay, now let's back to this positive definite matrices. So the first thing came from the quadratic forms. Quadratic form is of of this case ax square. Let's do for only 2 cross 2 even bx by square, or maybe how exactly ax square plus 2c 2bxy plus cy square, something like this it is. Actually the reason is, if you see that each term have the same degree, that is why the degree is quadratic form is there. Each term have the same degree. That many variables, how many is to depend on which order you are following. That many this variables came. So this is called quadratic form, and it is actually came. You can convert this the representation is like this only. A B B C it is. I think it is of this case only. And here it is. You can write xy like this, and here is xy like this. If you multiply, you will get exactly this one. And here this matrix is symmetric. So from the quadratic form, you will get always here the symmetric matrix. And now the positive definite case, for these forms only, the case is that, or generally a symmetric matrix you have, okay, if you have symmetric matrix, then there is a term that positive definite, negative definite, positive semi-definite, and negative semi-definite. And these all actually very easily you can verify it by the method of eigenvalues. If all eigenvalues are positive, not even 0, then positive definite. If some of them are positive and 0 is there, then it is positive semi word is there, because 0 is there, you can add the word semi. And the next is negative definite. Okay, if your all eigenvalues are strictly lesser than 0. Okay, and if it is some of them is negative and 0 is also there, then it is a negative semi-definite. You can follow this method always to decide that your matrix is positive definite, negative definite. Most of the time, sometime there is a method to get that your matrix is positive definite or not. It's depend on the order. Okay, you can just there is a, let's say these are entries as there, A B C D F G H I. Okay, there are so many tricks are there. The professor is actually told by this method, but from my side I am saying, if this is positive and this matrix is the determinant of this matrix is positive, determinant of this whole matrix is positive, then this is also a positive definite. Okay, but there are so many cases actually. If it is less than 0, then it is a bit confusing. The simple method is decide by the eigenvalues. It is positive, strictly positive, positive definite. Somewhere is 0, positive semi-definite. Strictly negative, negative definite. Somewhere 0 you are getting that negative semi-definite. This is what it is. Yeah, I will suggest you to follow this. Sometimes may ask in the 3 variable also, not more than that. Okay, in 3 variable, maybe it is of this kind: x square plus by square plus c z square plus 2 maybe d xy plus 2. Please check with that how you will convert this to, means how you will get the exactly symmetric matrix from here. Okay, so you can check it. So from again the same method you have to follow. You have to find the eigenvalues and decide that how you will get the, or how you can confirm that it is a positive definite or negative definite. Without finding the eigenvalues is, that is what I am. So then check with convert that in the quadratic form and check whether that always you are getting, output as a positive or not. What is a positive? Quadratic form have the, have a, we will say the positive definite when it is the all outputs are positive, and positive semi-definite means sometimes zero, and positive negative definite means negative. So if you fix with your without the eigenvalue, so you can check with quadratic forms and always getting positive or not. And the second method is what I said here, but even I have to check this method. I know for the positive definite, because you have to this entry positive, this determinant positive, the whole determinant is positive. For the negative case, I'm not sure that I have to check that maybe this is negative, this determinant is negative, and whole determinant is negative, then it is called negative definite. This is from my side I am saying, but still I have to check it. I think these are the way actually, but these are
Sir,
the
so it is positive. So the A would be positive. Then the uh, upper left corner 2 cross 2 matrix
positive
will have a positive determinant.
means determinant positive, correct.
Positive, right?
uh,
And and then the entire matrix should have a positive determinant.
a determinant
Right.
should be positive.
All the three segments should have positive values, right?
Positive determinant.
Okay, sir. Thank
For positive one, I know that is this is correct. For the negative one, I have to check. Sometime maybe in between negative or something. So I'm negative for negative, I'm not sure. But for positive one, this is totally correct.
Thank you, sir.
So this is what in week 6. I don't know how much all of you are able to get it. We stuck on the finding the singular value. We did a problem and slowly we stuck there and we did. But this is what the singular value. It's actually time take you, but in quizzes and all sometimes simple numeric would be given and you can easily calculate it. My suggestion is always go with the A transpose and A transpose A to find Q1 and Q2. Mean to say always go with to find Q2 follow A transpose A, and to find Q1 follow A transpose. Yeah, just convert them in, once you found the eigenvectors, get that they are orthogonal or not. If not, follow the Gram-Smith, and feel to find the Q1 and Q2, because whatever I did, that is a very lengthy process. Even I feel that is how much long it is going to be. And many times applying Gram-Smith is a bit tough sometimes, not sometimes, many times. So best way is follow this one to decide Q1 and Q2. Quickly we can decide from here. Only just need to find the eigenvalues, eigenvector. And the middle one is the sigma is the root of the eigenvalues. You can accordingly feel it, the root of lambda I. Okay. So I hope all of you tried it. I mean, so I have told the differences and one problem I solved. I hope all of you able to get it. That is what from my side even. Okay, that's all. Anyone have any doubt?
So for the second method you mentioned, we have to find the um, eigenvector and then we have to normalize it, right?
Normalize it.
Okay. And sir, one more question, like in
Yeah,
previous
finally just verify. Always verify this Q1 sigma Q2 transpose 1. Verify that A is getting or not. Otherwise, you have to check yourself. And so please verify it always.
oh, sir, and also in previous session, in one question you were able to just looking at the Q1, Q2, you were able to say that whether is it an SVD or not. Could you show an example and show that? Like, how you
Sorry.
did? Like in one of the previous sessions, like we were solving an I think practice assignment. You were showing how without multiplying everything, given Q1 and Q2, you were able to tell like is it a SVD or not? Can you?
Without multiplying.
Yeah, just like with the like it was a shortcut you were saying for exam. Like if you see three metrics like Q1, Q2, and uh, like it was
Actually, I didn't took this week 6, but trick is without multiplying is mm, without multiplying. How we can verify that is exactly SVD or not? No, I am not sure. Without multiplying, how will you say that it is exactly A you are getting? Or maybe Mayur sir have taken that, but without multiplying, I'm not sure that trick because.
okay. I'll recheck the
Hmm?
maybe I'll recheck the previous one. Like I think it was something like he was saying maybe if it is orthogonal Q1, Q2, you could guess like it was like eliminating other options. So some in that
Maybe yes. That is totally right. Yeah, elimination means check that orthogonality first. Very quickly check that vectors are the columns are orthogonal or not. And I said no, very quickly just do the inner product. That's why I'm emphasizing on the inner product. I mean, so check that columns are orthogonal or not. In real number, the checking the orthogonality means so in real number, sorry, in the real inner product, checking the orthogonality. You want to check two vectors are orthogonal or not, just do the direct multiplication, means coordinate wise multiplication, and add them finally. If you are getting 0, the columns are orthogonal. So very quickly you can check it even.
okay, sir. Thank you.
That could be used as a trick to eliminate the option. Okay, that's all. Thanks everyone. Thanks for joining. Okay.
Sir,
Yes.
I was asking for something. So, like, can you please prove that the eigenvectors of a orthogonally diagonalizable matrices are orthogonal to each other? I was searching for this proof, but I didn't get.
Means symmetric matrix have the symmetric matrix is orthogonally diagonalizable.
Yes, and they have orthogonal eigenvectors.
Then why you are searching? The spectral theorem itself tells you, no?
Yes, but then why do they have orthogonal eigenvectors?
So a spectral theorem, that proof itself giving that. If you see the proof of it, it is actually proving that it is spectral theorem is not just saying diagonalizable. It says the orthogonally means in the proof finally it will show that okay how the eigenvectors are going to be orthogonal.
Okay, sir. Okay, sir.
So it's don't look at the other theorem. Just see the spectral theorem. That is itself saying that vectors are going to be orthogonal. Sorry, eigenvectors are orthogonal.
Okay, sir. Thank you.
Yeah.
Sir, have you updated the PDF of PCA?
PCA, no. So yeah, next revision session we'll discuss in the next revision session.
Okay.
In the next revision session we'll discuss PCA. So probably Mayur will take so PCA and the next sorry week 6, sorry 5, 6 we discuss 7 and 8 we'll discuss.
No, I am talking about whether you have said I will update the steps in this.
Steps of PCA.
When you share the script and transcript of that lecture PDF, you have shared when you discussed the PC previously session.
Oh, okay. I didn't share it. So, okay, I will. This is the full MLF is actually I'm discussing all here. Maybe I will give this one to upload in. So here I think in the red one is today I have taken. Otherwise, one by one each day I took. Slowly we reaches. This is what the PC I have discussed, right? This is what you are asking.
No, it is I think provided on portal.
Oh no, so it is already okay. So that that is already I have given in the calendar. Did you check it here? This one. Oh, so I in front of you. So it is not available till now. It is okay, but here it is. See, in calendar I have given in front of all in the session. I showed you that from the calendar you can check. Okay, I didn't give to upload in portal. Okay, I think I have messaged him. Okay, from the host. Okay, it will be given, but yeah, you can find here from here this calendar.
Okay, okay, thank you.
26.
Okay.
Okay. Thanks. Thanks, everyone. Good night.
Good night, sir.
Thank you.